which is on the heat conductions. Now, in this topic, what we are going to look is how we can apply finite elements modeling in solving the heat transfer problems. Before this, most of the topic that we look, which is solving structural problem, but now uh, we try to look, or we try to demonstrate as well uh, the capability of finite elements in modeling other than structural problems. So in this case, we choose the steady state heat conduction problem, and we try to solve this using finite elements method. So this is actually to show you that the finite elements is just a mathematical approach, a numerical approach. It's just a mathematic that we can apply to now. We can apply it to a variety of engineering problems, which is initially these finite elements actually was developed to solve a structural problem, but now we can use finite element for solving complex structural problems. It can be used for solving fluid problem, heat transfer problems, and a few more other problems. It's just the matter of people often solve a fluid using finite volume instead of finite elements. So that's why this finite element is more popular in solving structural problem rather than fluid problems. So all right. Now let's we look in general what is heats. Actually, you may have done this in your thermodynamics course, but I'm not going to go in very deep detail on the explanations of the heats. Just a very brief, because you have done this before. All right, now I just read the slide, then I try to explain a bit if required. So what is heat? So as your revisions, heat is a form of energy. So there is an energy contained in the heat that is by virtue of temperature difference. So that's mean here, if we are living in a space where we have temperature difference, so there will be energy contained in that region. You know, we are at the aeronautics laboratory. We are not only working with aerospace aeronautics activities. We also at the moment working with our Japanese counterparts, with the University of Saga University in Japan, to develop systems, which is in our case for the Aero Lab, because I'm from aeronautics. I'm the aeronautics staff from aeronautics department. So our laboratory involved in this, what we call it renewable energy, which is we are trying to harvest. Before this, people harvesting energy from solar, right? From the radiation, solar radiation using solar panel. But in our case, we are actually working on are not very it have been established somewhere around the world, but it's totally new in Malaysia, and people are working on this in other part uh, of the world as well. Uh, for example, Korea is working on this, China is working on this kind of energy harvesting as well, which is we are actually trying to harvest energy from temperature difference between the surface and the deep water level in the sea. So the biggest temperature difference we can obtain, then we can expect we can get bigger energy out of it. So in between Malaysia and Philippines, I think very close to Sabah regions, I think the north of Sabah region, something like that, there is a very, very deep um, very deep sea level around that region, and where we can have quite a large temperature difference in that region. It's still in Malaysia territory. So we are working on what we call it a small scale system first, and then later on, which is to harvest energy for about 30 kilowatt, which is very small. And then when that system's success, then we will develop a big scale energy harvesting system, and it will be located around Sabah regions. So that's the long term, what we call it, research between us. So the Aero Lab is developing or look at the turbine system to convert the energies from the fluid. So in the system we have we use ammonia in the systems. There are a lot of system involved. So in the loops we have ammonia, then it will expand, it will condense in the system. So the flow of the ammonia in the system will force the turbine to rotate. Then this the rotating turbine later on will rotate the generator, so we can harvest the energy from from the from the generator. So that's roughly to yeah to expose you to what we at the university are doing. We look at this kind of new technologies, then later on we may operate it ourselves, or we sell it to certain industry to operate it. Yeah, so this is just to explain uh, the energy that contained in the region where we have temperature difference. You can imagine, even though small temperature difference is contains some amount of energy, it's just the yeah, whether we can use the energy or not, right? Because of the amount is too small, and the heat also is transferred. That means it flows. It has convections from higher temperature to a lower temperature region. So if now you are inside your house, the temperature, the ambient temperature outside of your house is slightly higher than inside your room where you stay now. So you can imagine that the heat is now trying to enter your house or your rooms, because it will travel, it will flow from the higher temperature regions to the lower temperature regions. And there are three types of heat transfer processes, which is the first one is by conductions. So you can refer to the figures. Conductions, let's say if we have a source of heat, we just apply to one location there. We apply to one location here, and then constantly we just apply it there. Then this heat will travel to the both side, to the left and to the right of this rod. Um, yeah, by conduction. And then second one is by convection. So when we supply heat to in this case of the kettle to the bottom surface of the kettle, so the heat is now by convection will hit the lower surface of this kettle, right? And then in the kettle we have water. We would like to boil the water. So when the surface of this kettle become hot and hotter, so the energy that contains in the hotter area is higher than the lowest one. So the water start to boil. So the boil, there will be a bubble develops. So the bubble will rise to the surface. Then this the rise of bubble to the surface, actually it bring the heats. Then the heats here will mix up with the surrounding the waters surrounding this bubble here. Then it will distribute the temperature in all direction through what we call it. This process is called the convections. And the third one is radiation. Radiations is a kind of process where we have, let's say this is the surface, or this is our Earth here, which is do not attach at all to the source of the heats. So we are far apart. But uh, this source of heat here has the temperature which is the greater temperature. So which is due to this very high temperature, this heat here can be sensed by this the Earth's surface, and this process is called radiation. So we have two systems that far apart, but the heat still can be transferred to from one to another through the process that we call it as the radiation. So this very simple explanation, and it says that, okay, in our course here, we limit our discussion to the steady state conduction for the first topic here. That means the temperature variation from one part to another is we consider it's a constant, or it does not influenced by the time, because we can imagine here, if we have we just place this rod here, which is we know the temperature of the rod, then suddenly we place the source of the heat, right? So then from there you can start taking your clock, then start measuring the temperatures variations or distributions around along this rod. So once you start ignite this what we call it penunuh Bunsen kan, kat sekolah dulu panggil penunuh Bunsen. So you actually So when you start ignite the things here, then the temperature will start to travel from this point to the right and to the left as well. And then the temperature keep varying from time to time. So this is what we call it as the transient transient process, which is we measure the variations of the temperature distributions in time. And in fact, in the real, it will change in time until we found that the temperature at one time or at one stage, even though you keep heat up this source or region here, you will, if you measure it, even though for maybe 1 hour, 2 hour, or 3 hour, the temperature will become constant. It does not change anymore in time. So that condition, we call it as that the temperature has reached the steady state condition. So it does not change anymore with time. So in our case, we don't consider the transient part. We just concentrate on this steady state conduction process in the heat transfer problem. Then we try to solve this by using the finite elements approach. So this is just another figure just to show you the three different processes in heat transfers. So yeah, this is just another example. Um, two regions, which is inside the house, and the ambience condition, which is this is the ambient outside of your house, and this is inside of your house. So yeah, this is the glass, the windows glass in four seasons, in the country with four seasons. And this is actually usually um, the new and the new house, new building will use this, what we call it, double glaze windows, which is we have two layers of glass to slow down uh, the heat transfer from one surface to from one region to another. I don't have these chances to live in this kind of house before when I was in the UK, because my house in the UK was actually developed during what they call it, I think 18th century, something like that. And that building has been gazetted as a historical building. So there is no um, the tenants or the owner of the building cannot make modification at all to the building, at least to the outside and look of the building. Inside, yes, you can have it. So my house before just have a single glass. So you can imagine during the winter, it is a very cool. It's very cool. It's like you are living in the refrigerators. And I have basements at the bottom below my house. So uh, the the cold air from the basements also, you can feel it's uh, yeah, due to the wind blowing pressure difference, then it entered into my room. So we have to burn a lot of gas to heat up the house. So with the two surface glass here, it can prevent the heat transfer to uh, from heat to transfers from one region to another. It's slowed down a bit. It's still cold, but it's slowed down a bit. You can save a lot of money from burning the gas, because you need to, maybe some of you have experience living overseas, so you can save some money, yeah, to yeah, to use your heater. There is a two type of heater actually, electric one and the water from the water boiler one. So the one that we use is from the water boiler. All right, now let's we look at this one-dimensional steady state conduction. Do you have any question, guys? All right, all right. Give me a second. All right. Now let's we look at this a bit of theory on the steady state heat conductions. So again, we will focus on the one-dimensional steady state conduction problems only. So this is our limitation for this course. It is the easiest heat conduction problems. So later we will see what the conditions that we have for the steady state conductions. So the objective here, which is to determine temperature distribution for the steady states heat conduction within the body, and also we may would like to know um, the amount of heat transfer, or in other name, often we call it as the heat flux. So so in terms of the governing equation, okay, we consider the heat conduction, which is given by Q. The unit is a watt per meter square, so watt per unit meter through a plane. So let's say we have a plane wall. So this is the left face, and then the right face on the right hand side. Give me a second. Sorry, guys. Yeah, everybody is now working at home. Okay, now we continue. So if now we consider that I have this plain wall and I take one small portions of this wall here, this small portion of size dx. So I enlarge it. So this is what we will see if we enlarge these figures here. So it mentions there an energy balance across a control volume. So actually this thing here, we can imagine we have a structures, a wall, which is in 3D, right? So everything must be in 3D. So if we can imagine it's something like this, energy balance across a control volume, which is the shaded one, shaded area, will give us QA plus capital QA dx. Okay, then this is equal to Q plus dq over dx multiplied by the area. So area here actually refers to the surface area of this left and right face. So this is actually the energy balance equation. So whatever comes into this surface, so it should be equal to whatever will be leaving this surface. So I'm not going to discuss further detail here. You can look into the thermodynamic or heat transfers textbooks. So if we apply this energy balance equations, then it will give us the terms to the internal heat generations, which is given by capital Q equal to dq over dx. So if we can imagine now, the amount of internal heat generated per unit volume is just equal to the gradient of the heat flux per unit area divided by uh, the length of the distance. Okay, the small distance that we consider So in this case here, since we are considering the small segment dx for these strips here, so we can obtain how much the energy generated in this within these strips. But of course, we are not solving small strip here. We may have several strips. So we have to solve for the first strip, then we solve for the second strips, fourth, fifth, and so on. Because we would like to solve the complete system, right? So we just take one strip here to develop the mathematical relations only. So it's mentioned there for one-dimensional heat conduction, the heat flux Q is governed by the Fourier's law, which states that the heat flux per unit area equal to the thermal conductivity of the material. So it's depend on the material we use, and then multiply by the gradient of the temperature within the area that we consider. So let's say uh, I have, let's say, the distance x here, and then I make a measurements. Okay, let's say I have the rod which is spanning from this to this distance only. Let's say from, I call it from x 1 to x 2, and then I measure the temperature along this segment or rod. Then I know at this particular end of my rod, the temperature is about this much, and the temperature here is about this much. Assuming the linear distribution, so we can plot the temperature distributions across or along this um, my, let's say we call it bar, right? Along this bar or along this segment. So this is the temperature. So if we take the gradient, so I have in the y direction, I have a dt. In the x direction, I have a dx. So the slope of this graph here, if yeah, because we know the material of the structure of the bar we use, let's say we use certain materials from the aluminum families, let's say. So we know the K. So if we multiply this constant value, which is the thermal conductivity of a material that we use, then multiply by the gradients of the temperature, then actually it will give us the heat flux Q. And the negative sign used here, which is due to the fact that the heat flow from high temperature to the low temperature regions. So I guess that when they develop this, they work from the low temperature to the high temperature. So once they prove that the temperature is, the heat is transferred from the high to the low temperature, so they reverse it by using negative here. All right, this is just two little bits explanations of the Q, the internal heat generated, and also the heat flux per unit area. Again, if you would like to go deeper in these definitions and explanations of the internal heat generations and heat flux, then I recommend you to review back your thermodynamics and also heat transfer course. All right, this is gene baptized Joseph Fourier. So as you can see here, the methodology that was developed since late of 17th centuries is still still valid in today's it's still valid today. I just wonder when I read some historical background or certain people, I still wonder how people at that time can come up with very useful methodology, very useful equations, which is not many people can do in 19th, 20th centuries. We have so many advanced technology. We have computer, even now computer in your pocket, your telephone, right? But not many useful equations is developed lately. as compared to at that time, 17th centuries, you can imagine what they have. Even computer, they don't have computer at that time. Kalau ada computer pun, you can imagine the first RAM computer, just berapa kilobyte je. They have to, yeah, the size is macam satu bilik kecil kan, size dia RAM. Sekarang ni satu terabyte dalam kamu punya poket je, tu pun kecil je kan. Dulu berapa byte je, kena angkut dengan kapal terbang nak, which is nak tunjukkan size dia tu besar macam kontena 8 kaki. Berapa kaki? Tak ingat lah. Yang small container, dia ada 2 size kontena tu kan, yang half tu. About that size, the RAM. Itu pun dah tahun bila dah tu, 19 something dah. This is, yeah, it's not only, yeah, if you read about the Muslim scientists, Chinese scientists, Indian scientists, European scientists, they're all very great. Some, just for one, one person, they can specialize in 2 or 3 disciplines, and they excel in all. Kita bukan nak katakan apa, saya sendiri pun I can't master, I can't say that I am good in my field at all kan. We still digging the information. Jadi bila kita dig, lagi banyak kita baca, lagi banyak kita tak tahu kan. Lagi rasa macam benda ni pun aku tak tahu kan. So that's the beautiful on knowledge. But if you can master one, then yeah, it is a very, very good lah. It is very, very good. And there is one guys, I think you his name pop up quite a lot recently. He is a Malaysian. He is Malaysian, which is he come up with one useful equation. Macam Fourier series lah, macam ni, macam Hooke laws, macam Fourier law. Tapi dia panggil nama apa ni? Fauza equation. Actually, the name of the equation is something else initially, but now people refer it to Fauza equation. Fauza tu nama ayah dia sebenarnya. Mak Saleh kan panggil nama ayah kan, Fauza. Nama dia lain sebenarnya. So Fauza equation. If you search for Fauza equation, then you will find him. Alright. So that is just to share some information with you. Dan kadang-kadang this equation kita bukan nak buat dia pun, tapi bila kita buat kerja, then dia tiba-tiba dia terhasil dengan sendirinya kan. Kadang-kadang kalau kita fokus memang nak buat benda tu, dia tak jadi. So bila kita fokus benda lain, tiba-tiba keluar I can use this equation repeatedly. It represented the non-dimensional units kan. Then benda tu berguna kan. Alright, and then we have this 2 q, which is equal to dq over dx, and we have the small q, which is referred to heat flux per unit area, equal to negative k dt over dx. So if we substitute this into 2 into 1, saya punya pen ni. So if we substitute 2 into 1, then you will get this equation. So we have, if we substitute 2 into 1, then the governing equations, new governing equations can be developed, and it must be solved with appropriate body condition. So this equation perlukan kita definekan boundary condition untuk kita selesaikan dia, untuk kita tutupkan the mathematical equation dia. So the Q is called a source when it is positive. Heat is generated. So kalau Q positive, that means heat is generated. And when the sign for the Q is negative, so heat is consumed by the systems. So this is just to recall back your knowledge lah on the thermodynamics and also heat transfer. I think your group pure mechanical, I think you took thermodynamic and heat transfer course, right? Something like that. All right, now let's look at the boundary condition. Actually, I would like to tell you the last two topic is the easiest topic in our course in these finite elements. Most of the time student akan score lah, many can score full mark actually. Tapi depend on the question lah, depend on the question. Tapi more of the time, the problem almost the same lah. Dia punya problem almost the same. So lecturer nak pusing-pusing soalan sangat pun, there's no much way to play around with the questions. So if you have a past semesters punya question, you do a lot of exercise, I can guarantee lah you can score in these last two topics. Tapi actually yang first topic hari tu pun senang juga sebenarnya. Actually 1D problem, cuma a lot of careless lah hari tu, a lot of careless. Hari tu yang a lot of careless, if I can share here, we would like to solve AE over L, 1, -1, -1, and 1, right? So we have already mentioned the structure is to be discretized using equal spacing. So when equal spacing, then you have to take lah, kalau L, dia punya panjang ni, untuk setiap elemen adalah L over 2. Dia punya elemen length. Tapi several students dia lupa nak gantikan L dalam equation ni, because this adalah untuk elemen. Untuk elemen. Kalau elemen nombor 1, length dia adalah L over 2 kan. So bila dekat sini salah, then yang kat bawah-bawah tu you can imagine lah. Actually lah, kalau in engineering practice, dia it's not that as strict as you are doing medics. Medics ni dia direct dengan human kan, dia direct dengan human. So any mistake direct to the human. Tapi kita ada one layer before human. We develop car, for example. Tapi car tu, kereta tu akan diguna oleh manusia. So kita bukan direct dengan ni. Kalau ada berlakunya failure kepada kereta tu dulu, which is kita akan buat testing kepada kereta tu terlebih dahulu kan. Kita buat kapal terbang, kita testing kapal terbang tu dulu sebelum masuk ke manusia. Tapi medik dia tak ada macam gitu, dia direct kepada manusia. Sebab testing kepada haiwan pun ada protes juga sekarang ni kan, kenapa kita nak sakitkan haiwan. Tapi it's direct to the life, medics. So even though it's not that as strict as a medic, but we have to make it quite strict as well, but not as strict as the kalau yang ambil medics lah. So that's why when this part wrong, basically actually dekat bawah-bawah tu you should get 0 lah sepatutnya. Tapi we still consider the methodology. Methodology actually is kalau method the flow dia betul, so kita still give the mark kan. Kalau kita bagi kosong terus, semestinya ada let's say berapa ratus orang student ni, 300, 400 lebih kurang orang student macam gitu. Kalau half of the student repeat, semester depan 400 tambah lagi 200, 600 orang kan. So so that's why yeah, sometimes we have to be fair as well. So it's just a mistake, but that mistake is what we call it a kind of severe mistake as well. Kind of careless, but it's a kind of a severe careless. Okay. As I mentioned earlier, this topic we are considering the heat transfer in one direction only. So sepatutnya kalau kita ada heat dekat sini kan, kita ada heats. So heat is not only travel in one direction, it actually travel up and down, left and right. Kalau in 2D, kalau in 3D dia ada ke sana dengan ke sini lah. Okay, in all direction actually. Okay, tapi in some cases, macam saya pernah cerita pasal wing aircraft dulu kan. In some cases, kita boleh modelkan wing tu sebagai 2D sahaja. It's still accurate actually. We have tested it for so many times. Other people have tested it so many times. It's still accurate. If we model it in 2D, even though the wing is in 3D. But we have to know where the wing section that we would like to model it, what the flow conditions around that particular wing section. So sama juga dengan heat transfer. Even though in the reality the flows, the heat transfer in all direction, but in some control cases, we can simplify it just in one directions. Alright, I think we stop here lah untuk hari ni, up to boundary condition. I just would like to inform you that our class on Sunday, the coming Sunday, will be replaced to Wednesday night. Macam yang biasalah, sebab hari Sabtu dengan hari Ahad, I have lecture for the part-time students. So 2 hari direct tu, pagi sampai malam tu kelas dia tu, boleh tahan juga tu penat dia. So that's why I unable lah to conduct lecture on Sunday. So we have to move somewhere on Wednesday night. So kita start around 9 o'clock after we have all finished our dinner. We free ourselves, so kita continue this topic. Actually this topic pun very short saja, body condition, and then temperature function exactly macam kita buat untuk 1D bar. Ini pun saya akan skip a lot ni dekat sini, benda yang sama je. Element conductivity metric, we will go very fast, and then we will, I think hopefully we can go straight forward to the some examples lah hari Rabu nanti. Because the implementations of this heat transfer problem, which is closely resemble 1D bar problem, cuma ada some modifications to the equation that we have to do lah in order to solve this problem. Alright, give me a few seconds so that I can share with you your attendance. Do you have any question, guys, to ask? So close at 10. All right, now I share with you the QR code. So please submit it as soon as you can scan it. And I think that's all for today. Selamat Hari Raya Mak Azhar dan Batin. Thank you very much for joining me this morning. And take care. Tak payah pergi berjalan mana-mana sangat lah. We try to lower down the numbers again. It's too much already, 6,000. Kita pun tak boleh nak expect siapa yang tepi-tepi kita yang the carrier sekarang ni kan. Carrier is, tak semestinya dia ada apa ni, ada symptoms. Alright, hopefully apa ni, kita jumpa lagi hari Rabu nanti. Okay, thank you very much and Assalamualaikum. Bye-bye guys.